So, I'm developing chemical AI. It means I'm devising chemical systems that somehow can approach some biological intelligent competencies. And so, of course, I'm inspired by your activity, by your research, your results. So, as I told you in my last email, I propose the concept of multi-scale chemistry because it's a way to mimic the multi-scale competencies of pluricellular organisms. So I cited your work and I told you, well, I'm proposing something that can be interesting also to you and your research.
Yeah, absolutely. That sounds very relevant. So please, I'd love to hear about it. Yeah, tell me what
Yeah.
you're.
Yeah. If you like, I prepare a presentation. So if you want, I can share this
Yes, please.
presentation. Yeah.
Yeah, go for it.
Okay. Thank you. Let's see. Okay. Okay. Can you see my presentation?
Yeah, perfect.
Yeah, very good. So, my name is Pier Luigi Gentili, and I'm professor of physical chemistry at the University of Perugia in Italy. And it's my great pleasure and honor to be here at the Allen Discovery Center at Tufts University and present my research on chemical artificial intelligence. That is an unconventional strategy for mimicking biological intelligence. So in my presentation, I want to answer three basic questions, three fundamental questions. First of all, why am I developing chemical AI? And I will highlight the necessity of facing the complexity of the 21st century global challenges. Then I will answer the question, what is chemical AI? So I will give a definition. And then I will present two achievements of chemical AI. One is a contribution to neuromorphic engineering in wetware, and it refers to a bio-inspired chemoacoustic system. That is an instance of multi-scale chemistry, as I mentioned before. And the other achievement is a contribution to quantum AI, and it refers to biologically inspired photochromic fuzzy logic system that extend human vision into the UV spectrum. And at the end, I will answer the question, which are the perspectives for chemical AI? So first of all, let's start from the first question, why chemical AI? So nowadays, humanity is spurred to face global challenges. And the list of these challenges, global challenges, is also included in the 2030 agenda compiled by the United members of the United Nations 10 years ago. Reaching the goals of this agenda means dealing with human beings and their societies, the world economy, the urban areas, the natural ecosystems, and the climate. These systems are instances of what we call nowadays as complex systems. So it's evident that whenever we face global challenges, we need to deal with complex systems. However, we experience seemingly insurmountable obstacles whenever we deal with complex systems. And these obstacles give rise to the so-called epistemological complexity. One obstacle derives from computational complexity. Many computational problems regarding complex systems are solvable but intractable. Examples are practical problems such as scheduling, the traveling salesman problem, but also problems of basic science such as the Schrödinger equation or the prediction of the three-dimensional structure for proteins. When these problems that are NP problems have large dimensions, we cannot determine their exact solutions in a reasonable time even if we use the fastest supercomputers in the world. A second contribution to the epistemological complexity derives from the recognition of variable patterns that are emergent properties of complex systems. Although the research line focuses on the recognition of variable patterns is particularly lively, we still lack the formulation of a universally valid and effective algorithm for the recognition of every type of variable pattern. A promising research line to face the epistemological complexity is natural computing. That is an interdisciplinary research line drawing inspiration from natural phenomena to formulate new algorithms, to propose new materials and architectures to compute, and new methods and models to understand complex systems, based on the rationale that any distinguishable physicochemical state of matter and energy can be used to encode information. And every natural transformation of these states is a kind of computation. Within natural computing, we distinguish two programs. In the first, scientists exploit the physicochemical laws to make computation, by knowing that any physicochemical law describes a forward causal event, and any forward causal event can be conceived as a computation, because the causes become the inputs, the effects become the outputs, and the law governing the transformation becomes the algorithm of the computation. In the second program, scientists mimic the information gathering and utilizing systems belonging to living beings. So we might mimic how cells compute, or how nervous systems, immune systems, and societies of agents compute. The research line of chemical artificial intelligence derives from natural computing and is trying to answer the following heuristic questions. Which performances of biological intelligence can be mimicked through inanimate chemical systems in wetware, in a liquid solutions, which is the characteristic phase of life? Traditionally, artificial intelligence is developed through two strategies. One relies on software running on current electronic computers or special purpose hardware. Such software either reproduces the thinking process when it is a flow of rigorous logical operations based on numbers of words, or it mimics some structural and functional features of neural networks to learn how to perform tasks from data, or it mimics some rational biological phenomena, for instance, the biological evolution. More recently, a new strategy to develop AI has been proposed that relies on reverse engineering neurons and neural networks in hardware. And such neural surrogates and networks in hardware are used as neuroprosthesis or to design brain-like computing machines, revolutionizing the von Neumann architectures of current electronic computers. More recently, we have proposed a new strategy to develop AI, that is the so-called chemical artificial intelligence. It relies on molecules and macromolecules that operate as if they were the hardware, but they are dissolved in liquid solutions, where phenomena such as chemical reactions, diffusion, migration, advection, convection, and chemical waves can occur. And these phenomena operate as if they were the software. In other words, the hardware and software of conventional AI are merged in the wetware of reactive chemical solutions. In this plot, I report the knowledge map of chemical AI, a three-dimensional graph projected on a plane. Along the x-axis, we have the chi domains that are molecular and supramolecular chemistry, system chemistry, and multiscale chemistry. As I told you before, with multiscale chemistry, I refer to all those chemical systems that manifest self-organization at different spatial scales and multi-level causality when appropriate macroscopic thermodynamic forces are applied. Such chemical systems, maintained in out of equilibrium condition by the thermodynamic forces, give rise to dissipative structures and forms of active matter. Multiscale chemistry is required to mimic the structural and functional performances of multicellular biological organisms, exhibiting multiscale competencies, as you demonstrated and proclaimed in your research. In the knowledge map of chi, along the y-axis, we have the chi paradigms that are biosensor, brains, and effectors. And finally, in the third dimensions, represented by the saturation degree of the green color, I report the biological intelligent competencies that range from sensing to perceiving, from computing to planning, from working to acting. Some of these competencies have already been implemented, and they are indicated in black. Some others have not been implemented yet. They are indicated in white. Presumably, they require a further development of multiscale chemistry to be within reach. An ambitious goal of chemical AI is the development of chemical robotics. A chemical robot is envisioned as a confined, complex molecular assembly that reacts autonomously to its environment because it has sensors collecting data about the environment and internal state of the robot. It has artificial neural networks processing the sensory data, making decisions, and triggering the actions of the effector models that can act upon the environment. The intelligent activities of a chemical robot should be sustained by an appropriate metabolic model. Chemical robots should be easily miniaturized in order to be implanted in living beings and interplay with cells and organelles to perform biomedical actions. In other words, chemical robots should become auxiliary elements of our immune system. But at the same time, we might think of deploying chemical robots in the environment to safeguard the environment itself and face problems related to energy and food supplies, as enticingly alleged by the futurist Kurzweil. The development of AI might have a curious side effect. It will probably assist human efforts to unveil the mysterious event of the appearance of life on Earth. The staggering event of the appearance of life on Earth has been described as a phase transition or sudden change from a completely abiotic world to a world where the first complex chemical systems capable of exploiting matter and energy to encode, collect, store, process, and send information to pursue goals somehow pop up. And now, after answering these two fundamental questions, why chemical AI and what is chemical AI, as I promised at the beginning, I want to present two achievements. The first is a contribution to neuromorphic engineering in wetware, and it refers to a biosphere chemacoustic system. Being aware that the computational power of any neuron relies on its dynamical properties, we exploit chemical reactions such as the Belousov-Zhabotinsky, the Briggs-Rosher, and the Orban reaction to mimic the excitable, oscillatory, and chaotic dynamical regimes of real neurons. Then we put these chemical reactions in communication through optical and chemical signals, and we can detect spontaneous spatiotemporal synchronization phenomena analogous to those occurring in real neural networks. Moreover, these chemical reactions give rise to the wonderful phenomenon of chemical waves that are autocatalytic reactions propagating through excitable media. And the phenomenon of chemical waves is widespread in the human nervous system. For instance, electrochemical waves propagate in the form of action potentials along the axon of a neuron for information transfer at the cellular level. And electrochemical waves propagate in the form of spindles in our cerebral cortex to consolidate and integrate memories during our sleep at the cerebral level. The Belousov-Zhabotinsky reaction, that is a catalyzed oxidative bromination of malonic acid in aqueous acidic solutions, gives rise to outstanding examples of chemical waves, as shown in this accelerated movie. And since the behavior of the busy reaction is strongly affected by mixing, we explore the response of its chemical waves to mechanical oscillations. In this picture, I report the experimental setup. We pour a T layer of the busy reaction on a polystyrene Petri dish, and then we apply mechanical vertical vibrations with frequencies in the acoustic range. And we found out that device, based on the busy reaction, is sensitive to vertical mechanical vibrations in the range 2010 Hz. So we propose this device as a biosphere chemacoustic system that allows the discrimination of 7 acoustic bands in the range 2010 Hz, as I'm going to show in the next slide. First of all, I report the behavior of an Ampertard busy reaction, where we detect spontaneous phase wave propagating from the periphery to the center of the dish and target patterns that can be either sparse or dense. When we apply frequency in the range 2650, we still detect spontaneous phase wave and target patterns But the mechanical vibration make the front waves of the target patterns more irregular. When we apply frequency in the range 650, 500, we detect a pacemaker of advection-induced phase wave in the center of the dish. And this advection-induced phase wave propagate anisotropically towards the periphery, generating a clover-type shape. On the periphery of the dish, we still detect spontaneous phase wave and irregular target patterns. When we apply frequency in the range 500, 200 Hz, we detect a vibrating annulus in the middle of the dish, and advection-induced phase waves are generated in this vibrating region, then they propagate towards the center, and then quite slowly in the rest of the solution. When we apply frequency in the range 295 Hz, we detect two vibrating regions, one in the center and one in the periphery of the dish, separated by a steady nodal region. Advection-induced phase waves are generated in one point of the vibrating peripheral region, and then they move towards the opposite side, engulfing the nodal region. When we apply frequency in the range 95, 50 Hz, we detect a grid of cells that is a Faraday pattern. This grid of cells is generated by standing waves propagating orthogonally with respect to the vertical mechanical vibration. And the amplitude of the oscillations on the periphery is larger than in the center. The advection-induced phase waves are generated in one point of the center, and they spread radially towards the periphery. When we apply frequency in the range 50, 15 Hz, the grid of cells, the Faraday pattern, is now uniform. The dimensions of the cell constituting the grid increase by lowering the acoustic frequency. And advection-induced phase waves are generated in one point of the periphery of the dish, and they move quite quickly towards the opposite side, sweeping the entire solutions. And finally, when we apply frequency in the range 15, 10 Hz, the dimensions of the cell constituting the Faraday pattern are so large to fragment the front waves of the advection-induced phase wave that appear irregular. We observe that the velocity of the advection-induced phase wave is apparently dependent on the acoustic frequency, as we can see in this plot. The lower the frequency, the faster the propagation of the advection-induced phase wave. The interpretation of this dependence was possible by invoking the network of cells model. The solution of the busy reaction can be described as a grid of micrometric open reactors exchanging chemicals through diffusion and advection. The vertical mechanical vibration affect the chemical coupling between these micrometric open reactors. And the lower acoustic frequency guarantee a more extended chemical coupling, the formation of larger clusters, and hence a faster propagation of the advection-induced phase wave. And the simulated velocity are in agreement with the experimental results. This system, as I anticipated before starting this talk, constitutes an instance of multi-scale chemistry, because the dissipative spatiotemporal patterns we observed at the macroscopic level are due to a multi-level causality involving the macroscopic level, where we apply the vertical mechanical vibration, the mesoscopic level involving the micrometric open reactors, and finally the molecular level involving the busy reaction, the molecules participating in the busy reaction. Tricky outputs allows the discrimination of 7 acoustic bands in the range 2010 Hz. First of all, the chemical waves. And the frequency of these chemical waves are 3 to 5 orders of magnitude smaller than the mechanical, the acoustic frequencies. Furthermore, a second key output is the dependence of the advection-induced phase wave velocity on the acoustic frequency, described by this bi-exponential function. And finally, the third key output is the dependence of the Faraday wavelength on the acoustic frequency, described by this equation and shown on this plot. We can find some analogy between our biospire chemacoustic system and the human ear, because in the human ear, the cochlea is a transducer of mechanical energy into electrochemical energy, and we have tonotopic representation of the acoustic waves along the asymmetric basilar membrane. In our biospire chemacoustic system, the Bezier reaction is a transducer of mechanical energy into chemical energy, and we detect peculiar spatiotemporal patterns as a representation of different acoustic bandwidths. Now, after presenting this achievement, I promise to tell you a second achievement that is a contribution to quantum AI, and it refers to biologically inspired photochromic fuzzy logic system that extend human vision into the UV spectrum. So first of all, quantum AI is a recent research line derived by merging quantum computing and artificial intelligence and expecting to observe synergistic effect by this mixture. In quantum computing can speed up artificial intelligence, but at the same time, artificial intelligence can support the development of quantum computing, for instance, in error mitigation or in quantum circuits optimizations. Traditionally, quantum AI relies on qubit. In our case, we are presenting a contribution to quantum AI that relies on thermalized quantum states that allows the implementation of molecular fuzzy sets, and they allow us to process fuzzy information, as I'm going to show you in the next slide. But first of all, I want to recall some basic idea about fuzzy logic. Fuzzy logic, everybody knows that reproduces the exclusive human features of making decision, using deductive reasoning based on qualitative information expressed through the words of natural language. Any nonlinear cause and effect relationship involving input and output variables is described through syllogistic statements of the type if, then, wherein the graduation of the variables is achieved through adjectives. But adjectives are fuzzy sets that granulate and graduate the numerical values of both the input and output variables. For instance, everybody knows that a fuzzy set is different from a classical Boolean set because an item can belong to a fuzzy set with a certain degree. That can be any real number included between 0 and 1. As an example here, I show the granulation and graduation of the variable temperature in 4 fuzzy sets. But we must be aware that the number, position, shape, and graduation of the fuzzy sets are context-dependent features. Probably the most iconic success of fuzzy logic is its capacity to control the remarkably unstable inverted double pendulum. And in my view, we can state that a living can be imagined as unstable as the state of an inverted double pendulum. Any living being succeeds in surviving when it processes fuzzy logic at different spatial scales, from the molecular up to the organismic level. Fuzzy sets are implemented at the molecular level through micro-heterogeneous chemical systems. What does it mean? When a chemical compound exists as a collection of distinct conformers and/or experiences microenvironments with distinct physicochemical features, is describable as a quantum mixed state through this equation. And in this equation, with these raw quantum mixed states, Wi prime represent the probability of the height wave functions associated with one specific conformer and/or peculiar microenvironment. As an example, I show here this compound. It is a merosanine. It's a pretty flexible structure, so it can exist in many conformers. And each conformer has its own wave function. But this conformational distribution of the merosanine can also be conceived as a molecular fuzzy set. In this case, the equation defines the quantum mixed state, the Wi prime appearing in this equation, represent the degree of membership of the height wave functions to the molecular fuzzy sets. And the amount of information encoded by a molecular fuzzy set is given by this equation that depends on the wave functions appearing in the definition of the quantum mixed states, and of course, their relative weights. It's possible to process fuzzy information when physical and chemical inputs modify the Wi prime values, and hence fuzzy enter. And I show you an example by presenting the behavior of this thermally reversible photochromic compound, a spiroxazine that upon UV radiation gives rise to the merosanine. But the merosanine is metastable, so if we discontinue the irradiation, we have a spontaneous recovery of the original structure. And this structural change is accompanied by a spectral change, a significant spectral change, because the spiroxazine is uncolored, whereas the merocyanine is colored. And we record the appearance of a band, a peculiar band in the visible region. If we record how the absorbance in the visible region changes over time, we detect an exponential growth up to reach a plateau that corresponds to the photostationary state. Of course, if the radiation is steady, is stationary. And then as soon as we discontinue the radiation, we have a recovery of the original state, the equilibrium state, through a bleaching kinetic. Since the merocyanine is a pretty flexible structure, it is reasonable to fit these bleaching kinetics using polyexponential function. In my view, a good method to determine the best fitting function is the maximum entropy method, that is maximally non-committal, and its output is the least bias estimate possible on the experimental data. And I'm going to show some results. Here, for instance, I report the weights of different bleaching kinetic constants recorded for the merocyanine dissolved in pure ethanol at different temperatures. We can observe that the higher the temperature, the faster the bleaching process, and the broader the distribution of the bleaching kinetic constants. It means that the temperature is enough to affect the conformational distribution of the merocyanine. But we can affect the conformational distributions also through chemicals. For instance, injecting glycine, we detect that the glycine, the amino acid, has a double effect. It slows down the bleaching process and it shrinks the distributions of the the distribution of the bleaching kinetic constants. And this double effect is presumably due to a supramolecular interaction between the amino acid and the zwitterionic form of the merocyanine. So it's evident from these results that the conformational distribution of the merocyanine has context-dependent features, like any other fuzzy set. And the manipulation of this conformational distribution is a way to process fuzzy information, but is a form of quantum parallelism because we are manipulating wave functions associated with the different conformers. We can increase the degree of computational parallelism by preparing mixtures of distinct quantum mixed states. That means preparing mixtures of distinct molecular fuzzy sets. And for the selection of the chemical composition of these mixtures, we should be driven by the process of granulating the physicochemical variables. In this regard, a remarkable example is offered by human color vision. In the center of the retina, we have three types of cones, the so-called red, green, and blue cones. All these cones have the same chromophore, that is 11-cis retinal. However, the three types of cone differ in the position of the lowest energy absorption bands for the chromophore, because the proteins embedding the chromophore differ in the amino acid composition. These three absorption spectra are associated with distinct vibronic wave functions, and they are three molecular fuzzy sets granulating the visible regions. Lights having distinct modalities, distinct spectral composition, belong to these three molecular fuzzy sets at different degrees. And the collection of these different degrees constitutes the first clue to distinguish you in our brain. The granulation of the visible region is a form of quantum parallelism that confers humans the capability of distinguishing around 200 U's. To test the validity of this description, we decided to follow the same approach, and we devised biologically inspired photochromic fuzzy logic system that extend human vision into the UV spectrum. So we synthesized a collection of 5 thermally reversible photochromic compounds. Each compound has its own absorption profile in the UV, and we can state that each compound shows at least one characteristic absorption band for each of the 3 UV regions. Furthermore, each compound produces a peculiar absorption band in the visible region. The hue of color generated by one single photochromic compound is always the same, whatever is the excitatory wavelength in the UV. But we can prepare mixture of these compounds, 3, 4, and obtain at the end a system capable of discriminating the 3 UV regions, UVC, UVB, and UVA, by giving rise to colors having peculiar hues. For instance, the solutions containing compound 1, 2, 4, and 5 at specific concentration becomes green when irradiated by UVA, gray when irradiated by UVB, and orange when irradiated by UVC. So now I want to conclude my presentation presenting some perspectives for chemical AI. Chemical AI refers to the unconventional strategy for mimicking biological intelligence in wetware, which is the characteristic phase of life. So first of all, chemical AI and chemical robotics will help humans explore and colonize a fully investigated space so far, that is the molecular world. Decolonization of the molecular world will provide tools to effectively combat poverty, clean up the environment, overcome diseases, and extend human longevity. Moreover, trying to obtain intelligent chemical system from scratch can help understand intelligence and life. We are aware that chemical AI and chemical robotics are in their infancy, but we believe we need a productive interdisciplinary collaboration among chemists and specialists of other disciplines to succeed. This is the reason why I hope that this meeting could be the starting point of a fruitful collaboration with your group. So finally, I want to mention and acknowledge my current collaborators, my young resources, my students, my university and European Union for the financial support. And of course, I thank you, Mike, for giving me the opportunity to present in your prestigious Allen Discovery Center. Thank you, Mike.
Thank you very much. Super interesting. Lots of things for us to talk about. I like all of it. I like the biomechanical aspect, the vibrations. We've been doing a lot on that lately too in other contexts. So there's a lot here for us to talk about. Okay. Should we? Do you want to start with anything, or shall I just fire off some ideas?
Yeah. We can start. Yeah, if you want, we can continue. Yeah.
Okay. Okay. A few things. First of all, have you tried apply to these chemical networks? Have you tried applying any of the recent metrics from information theory? You know, things like causal emergence, any of that stuff. Have you done any of that?
Not yet. So we can.
I think it would be very interesting. So we have tried it with gene regulatory networks, which are also these kinds of models of, and now we're doing living ones, but first the models, and there's some very interesting properties of the different metrics, the different surrogates of phi and things like that. Yeah, that exist in random networks and then that exist in networks after they've been trained. So that's one of the things we do is we try to train these gene regulatory networks, partly for the biomedical purposes, partly just to understand kind of the origin of basal cognition, right? And I think you might it might be really interesting in your data to actually apply it. Federico Pagozzi in my group, who's doing all this stuff, is writing up a primer on how to do it and to make it easy. So if you want to do that, we can connect and we can try to analyze some of your data.
Yeah, it would be great. Yeah, why not? Yeah, great.
Both spatially and temporally, and I have a feeling that you will find in some of these cases you will find some significant phenomena as these emergent causal emergence metrics arise.
Very good. Yeah. This is good. This could be a way to develop multi-scale camps, right? Because
exactly. Yeah.
Exactly.
Yeah. And so you could do this. You could look at this at different levels, like Eric Hole in our group does to see which level is doing how much of the causal work and things like that. So I think that would be very interesting. What are your thoughts on this as far as this relates to the other question, because we're looking at it from that perspective, on the origin of life? Do you at least the biological version? Do you have any kind of a biorealistic scenario that you can look at that that people think are relevant to the origin of life?
I think I'm still working on it. I mean, I don't have results to show in that area, but I think it's the right time to broaden the scope of thermodynamics, because I feel there's something missing in thermodynamics, because we have Shannon entropy, no, but it's in terms of probability. And since I'm fond of fuzzy logic, and I'm fond of fuzzy logic because somehow it is capable to introduce the semantics in science. It's not easy, you know.
Hmm.
So the next step would be somehow to introduce the quality of information also in thermodynamics.
Hmm.
Yeah, I rely on thermodynamics because, if we can explain the so-called phase transition occurred at the origin of life in thermodynamic terms, will surely have something relevant to show to the scientific community, because thermodynamics is cross-disciplinary. So it has the systemic approach it uses is surely worth being pursued in any field. So um, again, I don't have a particular theory. I'm just reading all the theories proposed by other scientists, and I'm thinking that the right direction is to somehow explain that phase transition in thermodynamic terms. This is my point of view.
Yeah.
Uh,
Yeah.
I
Because
still need, yeah, still need to work in this direction, but I don't know if you agree with this idea or not, and we might also think of developing something together.
yeah, yeah. I
With
mean, so I'm not an expert in, of course, in thermodynamics, so I don't know how much I can add to that part. But I do think this is the right way to go. And also, what's clear from the kinds of things you just showed, and from work of like a Walter Fontana on probabilistic inference in chemical networks, and from our stuff on GRNs, that aspects of cognition show up extremely early. They don't need cells or genes or brains or any of that stuff. They're sort of much more basal, and that's kind of they emerge from I think probably patterns of mathematics and physical phenomena, and very early, which seems to me, and I mean, this is obviously not a mainstream opinion, but I think mind is there long before what we recognize as life, and we should be able to, at the origin of life, in these origin of life scenarios, the chemical ones, or the physical templating ones, or any of them. I have a feeling that we would be able to identify the kind of phenomena that you were talking about in your introduction. So I think that would be interesting. I've been talking to people. What I don't have is a particular model, and I just need a anybody's sort of plausible model of the events at the whatever this current thinking is about the origin of life, and then we can do all these analyses, right? We can try training the networks. We can try doing these kinds of phi metrics, and the kinds of things that you were just showing. We can do all of that.
Yeah, exactly. For instance, starting from chemistry, so we start from inanimate matter,
Yeah.
and we want to approach the competencies of living matter.
Mm.
Could be a way to see which are the least the most important ingredients to detect that phase transition from non-living to living, as you say, from non-cognition to cognition, right? So by assembling different components, we should maybe one day to detect the critical point to have that phase transition from non-living, from non-cognition to cognition, from non-living to living somehow. Right.
Yeah.
Yeah, exactly, exactly.
Yeah, I think I'm sort of visualizing. I need to make the slide. This is a slide I haven't made yet. Of typically you see when they stack the sciences, right? They sort of go physics, and then chemistry, and then the behavior, then biology, and then behavioral science, and whatever. But I actually think the behavioral science overlaps all of them, and it's there from the very beginning, and all these other things come up. It's there across the whole thing. and finding these kinds of things at the chemical level, I think is very important.
Yeah.
Another thing that we should talk about is one of the ways to envision what you showed today using, for example, using the vibrations is as a way to communicate with the system, right? So any system on the cognitive spectrum, you should in some way be able to communicate with it. And we are developing an interface with AI in the middle, which may or may not be necessary for some of these things, but basically an interface to let extremely divergent kinds of minds talk to each other. So not just cells to bacteria or xenobots to plants, or I mean that too, but some really weird, just making these cognitive cyborgs of some really weird things. Some of them are living, some of them are simulations, some of them are mathematical objects, some of them are AIs or robotics or whatever. So what would be cool is to set up and we have a paper now that is in review at A-Life around xenobots communicating with various things, and by the way, a paper that just came out look at using vibration to communicate with the xenobots. So in a very simple way, there's more coming, but just to show that that they behaviorally respond to certain kinds of sound stimuli. So it would be interesting to set up a hybrid system where some of our systems communicate bidirectionally back and forth with your chemical systems, and what kind of dynamics can we start to see in the chemistry if it's driven by signals from let's say a more advanced biological system and vice versa. What would the mutual interaction? What do you think about that?
Yeah, that could be very nice. We might, because this the chemical reaction that I show you, probably the Belousov, Zaputinsky, and similar reactions, they can reproduce the dynamics of neurons. So we can establish this communication, this chemical communication, or maybe also optical communication if it is possible, and see if there is a feedback between these the two systems and detect. This is
Yeah, we could also the fact that we are separated geographically, we could turn that into a feature, and we could have them communicate over the internet. So as long as the latency is not too bad, which I don't. What is the time? What's the real time scale of your system? How fast do these things change?
The oscillations of these reactions can occur in the range of a few seconds up to
Great.
tens of seconds.
So that should be fine. So we could set up an internet-based protocol to have a system in our lab, have a system in your lab, and the whole thing can be one giant brain. We'll make an interface for it that's kind of like our corpus callosum, right? To let two things, right? And we can see what the collective. We can look at I don't know. We'll look at the mutual information between them. We can look at some of these phi metrics. I think that would be really neat to add to the repertoire. I will say also that we have another project using developing AIs that will talk to cells. So allow you to talk to cells and gene networks and pathways in language, in regular language. And so for biomedical purposes and whatever, but they also raise these interesting questions of what happens when you add a linguistic interface to a cognitive system that's good at doing certain things, and then you put a semantic interface on it. I wonder if we could apply some of those to your systems, and you could talk to your BZ reaction and give some commands and get some information from it that way.
It sounds good. Yeah. I'm playing with music right now, this system, but I like the idea of using also some sentences, so some pronouns by in different. Yeah, it would be a good idea. Yeah.
Music, yeah. I mean, music is very interesting. We've seen we've done music with Physarum, the slime mold, and that thing definitely has preferences over which music it likes and which one it doesn't like, and it has all kinds of behaviors when it encounters it. Have you found, can you say that certain pieces or certain genres of music or whatever are treated differently by your system? Does it have
The system reacts in a different way depending on the kind of music. So changing the author, the composer, the system, the music, the complexity of the music changes, and the response of the chemical system changes as well. Of course, we cannot say he likes that or it doesn't like that kind of music because it's not a living being, but we can discriminate.
Well, what you can do, and with this is something we're doing too, is you can set up an instrumental learning assay where you don't know what it likes until you give it a chance to choose. So if you give a system a chance to either turn the music on or off by its actions, or by switching and let it give it a chance to switch between different types of music, you might find that if you just let the thing tell you what it wants, you have to figure out a mapping, right? So which kind of patterns are interpreted as, okay, change the music or turn the music up or down or whatever. So you make some sort of mapping, and then you see if your system actually makes use of it to control its environment. Like we're trying to make things like that to have cells self-medicate with certain kinds of drugs or ask for media changes in the in their environment or whatever. It's just like it starts as biofeedback, but it becomes an instrumental learning task. So I bet you could do the same thing here. I bet you could have the reaction choose its own music.
Yeah, yeah. I like this idea. Yeah, I didn't think about this aspect. Yeah, good.
Yeah. Okay, and one last, I guess, idea that I was having regarding the fuzzy logic aspect of it. Have you seen the stuff from Patrick Grimm from the 90s?
Can you tell me more about it?
Yeah, what he did was it's super interesting work. He's a philosopher, I think at NYU, if I remember correctly, and what he did was this. He was looking at paradoxes like like logic paradoxes, like this sentence is false, that kind of thing. And what he realized two things. One is that it's only a paradox if you take away time and try to insist on one frozen value, because then you don't know what that value is. But if you give it time, what you end up with is an oscillator that just goes true, false, true, false, true, false, right? It's fine. If you give it a time axis, you can just evaluate it, and you get this this sort of square wave, right? And then what he did was he said, okay, so now let's make it fuzzy, and so now you can have sentences like this. Sentence X can be, I am, as 50% as true as sentence Y, and sentence Y is, I am false unless sentence X is more than 30% true, something like that. And once you make it fuzzy, you can have these self-referential sentences, and now you can now they become a dynamical system. You can plot them. They have a shape. So some of them converge onto a stable value. Of course, some of them don't, right? They are cyclical, or they have strange attractors. Some of them are fractal. But what he developed is a mapping, a morphology or a shape, or if you give it time, a dynamic for these sets of logic sentences, and write them being fuzzy. And I think that's really interesting, because that's another link between formal properties of sentences and logic and statements about the world and so on, and these kind of dynamics that you have here. So I could even imagine going backwards, and like you have a reaction, you have a chemical reaction. So imagine if Grimm's formalism is the interface between the dynamics that you have and language, such that I can have sentences in the language that become translated into dynamical systems that look perhaps like, for example, like the BZ kinds of things, right? But could we go backwards? If we can go backwards, we can look at the dynamics you have and say, okay, what set of sentences does this represent? And it's not going to be a one-to-one, of course, but let's say the simplest or something. Maybe there's a way to choose, right? The simplest one. So what is it literally trying to say to you, right? When you have a particular chemical reaction, what is the language that it maps to in Grimm's formalism? I think that might be kind of neat.
Yeah. Yeah, I need to think about that. Thanks for the suggestion.
Yeah.
Very important. Yeah, yeah.
Yeah. So yeah. So those are some thoughts. So I guess I can flesh some of those out in a little bit more detail. But it sounds like any of these we could do.
Very good. Very good.
Yeah.
I'm, yeah, it would be very, very nice. Yeah.
What do you think? Yeah, the two kinds of things that immediately come to mind that might be relevant um, to this work. One is some of Lee Cronin's stuff on chemical computation, and I don't know exactly. I haven't followed all the details. I don't know exactly where it stands, but I mean, I know he's working on chemical computation. And there was another one I was going to ask you. What's the stuff on droplets? The chemical robots. What do you think about those kinds of things?
Yeah, they are alternative approaches to contribute to chemical robotics. For instance, the liposomes, micelles, and the oscillatory chemical reaction
Mm,
embedded in these systems constitutes neural surrogates or surrogates of cells, biological cells. And so they are also studying the self-replication phenomenon of these systems. So regarding Cronin, Cronin is developing especially AI in chemistry, we might say. It's not a truly chemical AI as I propose.
right.
Yeah, that means he is using traditional artificial intelligence algorithms to develop organic synthesis or no similar experiments typical of chemistry. So it's more AI in chemistry rather than chemical AI
Mm,
as far as the Cronin's research is concerned. And so there are different groups working on this area of chemical AI. For instance, tomorrow I will attend a workshop in Japan online, and they are developing the so-called molecular cybernetics towards chemical AI.
mm,
So they propose especially biomolecules as uh, let's say, neural surrogates, although because of macromolecule, biomacromolecules can have feedback effects, like, they have not only they are different sites, so they can react to different substrates and change their behavior depending on the chemical composition of the environment. So they design artificial neural networks using macromolecules or assemblies of these macromolecules, and also they propose these macromolecules as effector modules, so they can perform a mechanical work at the molecular level. This is the original idea in molecular cybernetics, to use macromolecules to perform mechanical work at the molecular level. Uh, so it's not the same I presented in my seminar, but they are parallel research routes that can contribute to the development of chemical AI.
mm-hmm.
Yeah, yeah, exactly.
And do you think that what does the field look like right now? It sounds like, I mean, there's a conference. Sounds like there's enough people that this is like an emerging
Yeah,
field,
yeah.
right?
There are different research group worldwide working on this area. Not too much so far because it's more AI in chemistry rather than chemical AI. AI
That's it.
in
Yeah.
chemistry is now on the verge of growing, no, exponentially, is rocketing the application of AI in chemistry. But there are groups like me working in this area of chemical AI, and I think it's interesting because, as I told you, we can understand more deeply phenomena like life, like intelligence, like cognition. So it's a bottom-up approach to cognition and intelligence and life. So as a chemist, we start from single molecules, we assemble them. And I think that the idea of developing multi-scale chemistry inspired by your activity, your results in biology, it could be a new pathway to approach the biological intelligent competencies. So it's promising. Of course, just it's, multi-scale chemistry is used in computation, in
Yeah.
computational chemistry, because to mimic biology, to mimic biological systems, they use different computational paradigms depending on the level of description. So, for instance, at the molecular level, they use quantum chemistry. But if they go to the mesoscopic level, they start to use mechanical physics, classical physics. And because of course it becomes too cumbersome to use quantum chemistry even at the mesoscopic level. And
Mhm.
they call that approach, they call onion approach because it's like an onion of different levels, no? Quantum chemistry at the molecular level, classical physics at the mesoscopic and macroscopic level. And if we now start to develop this multi-scale chemistry in real experiments, it could be a new way to achieve self-organization, applying macroscopic thermodynamic forces in properly designed chemical systems, because we must maintain any inanimate chemical system very far from equilibrium, the thermodynamic equilibrium, to observe the spontaneous phenomena of self-organization in time and space and approach the performances of biological organisms. So this is for sure. This idea, of course, comes from Prigogine, no? Who started to develop the principle of out of equilibrium thermodynamics. And this is the reason why I told you that we need also to develop more that part of thermodynamics, because we still fail to describe properly life at the thermodynamic level. Something is missing in that part. Uh, so
It seems also kind of a very related area to some of the reservoir computing stuff, where they use these. And so the question to me is, how what aspects of the reservoir are you actually taking advantage of? And I mean, degrees of freedom is one thing, but if the reservoir is active and a little bit smart, can you, right, can you do better? Yeah.
yeah,
So I wonder these kinds of things that you have here. I wonder if they would make interesting reservoirs.
yeah, it's of course it's a field, an approach in the so-called neuromorphic engineering, right? Because you have reservoir mimicking a neural surrogate, a neural network, no,
Yeah.
right?
Yeah, I
Yeah,
mean, I don't love the neuromorphic name because I think the thing we are trying to mimic is not neural at all. It's much, I mean, yes, neurons do it too, but it's a much more fundamental thing. I don't, it's not about chasing the precise architecture of the brain or even of neurons. It's a much more fundamental phenomenon.
yeah, yeah, yeah. That's